Welcome to today's webinar. Today's webinar is going to be on paralleling concepts. We're talking about the paralleling of standby generators. So I thank everybody for tuning in. Let's go ahead and get started. Now, this is our little icebreaker here. You might be an engineer if you use an RPN calculator, or if you know the glass is neither half full nor half empty, it's simply twice as big as it needs to be. My own opinion is the glass is always full. Sometimes it's just half full of water and half full of air. These are the things we're going to talk about, but you see we're going to move ahead a little quicker than what is shown on this. This typically takes an hour and a half. We're going to do it in 45 minutes. That's pretty typical of all the presentations that we've done over the last few weeks. I hope that's okay, but we tend to move pretty quickly. And of course, we make the slides and the presentations available in case you want to go over them at your own pace. Now, what is paralleling? Well, first of all, let's talk about generator to grid paralleling. I was the director of engineering at Geneva Steel. We had a 50 megawatt generator, and we paralleled to the utility grid. That's kind of a whole different thing that we're going to be talking about. When you parallel to the utility grid, the utility controls the frequency. The utility really is so big in proportion to that generator that it controls pretty much everything in the power distribution system. And your job is just to decide how much power you're going to put into the grid. That's a whole subject in and of itself. And so we are not going to talk about that. Typically, if you're using a standby generator like a diesel generator, the cost of generating power for you is going to be higher than what the utility can buy that power for through big power stations and dams and such. And so it doesn't tend to make sense for us to try to use a standby generator to feed into the grid. Now, it is becoming more popular for people to use generators, particularly natural gas generators, to generate power into the grid only when there is a peak demand problem in the grid when they're running out of power. And what they typically do there is they simply take the plant off the grid, put the plant on the generator. So you simply take load off the grid. You don't actually generate into the grid, but it certainly is possible to parallel with the grid. And maybe one day we'll do a presentation on that alone. Another type of paralleling that we're not going to talk about today is a paralleling that you use in a closed transition transfer switch. We call those make before break transfer switches. In that case, if you're running on the generator, you close into the utility, and for about 100 milliseconds, the utility, the load, and the generator are all paralleled together, which is typically a no-no for a standby generator. But as long as they're in phase, 100 milliseconds, this is very commonly done. You can also have soft load closed transition switches in which you will have that paralleling take place for maybe 10 seconds. And we will cover these things in a future seminar on transfer switches. Today, we're going to talk about the paralleling of standby generators. So here's a couple of generators. Now, in this particular example, we have two 500 kilowatt generators shown in the picture there. The question is, how much total power do we have? Well, like putting a couple of horses in a yoke, how much do you really have two horses of power there? How well are they sharing that load? Or is one pulling harder than the other and they're not balanced? So it turns out in all paralleled systems, those generators parallel very effectively. And so we simply add them together, and two 500 kilowatt generators will be the same as one 1 megawatt generator. Now, that's the case in terms of continuous load. What if you had a motor start of a very large motor? Let's say you had a 500 horsepower motor and you wanted to start that. You would typically need about a 1 megawatt generator to start that across the line. Could you start across the line with two 500s? And the answer is yes, of course you could. They will work just as well in that situation as they will in the continuous running mode. Now, why would you use a parallel system? Well, the number one reason is reliability. It is not the only reason. There are lots of reasons to use parallel system. And as we go through there, the presentation, you'll see a lot of advantages. But the number one is reliability. So how reliable is a generator? Well, that's not a subject, that's not a number that anybody actually publishes and hangs their hat on. Generac says generators are about 98 to 99%. That may be a little optimistic, quite frankly. And that comes from a government study showing that their generators were 98.2%. Well, so let's assume that it's 98%. That means one time out of every 50, that generator is not going to start. Now, in reality, I believe that reliability is probably a little bit less than that. But in the case of it being one time out of 50, if you have a hospital, certainly one time out of 50 is not going to be very acceptable. So we use what's called N+1 reliability, and N+1 would mean you buy enough generators to get the power that you need. That would be N, and then you add one more, so that if any one generator in that system fails, you will still have full power. Now, the other way you can do it is you can buy the number of generators that you really need, and if one of the generators doesn't work, you can simply take off some of your less critical load. But that's the number one reason for paralleling generators, to get a reliable system. In general, if you have one generator, you should plan on what you're going to do if that generator doesn't start and it's in the dark. If you have more than one generator, it's pretty likely, very, very likely, that you will never be in the dark for your lifetime. Now, there's one application that's more critical than hospitals. That would be casinos. And I'm only half joking there. If you go to casinos, they spend a lot of money on their standby generation. The last thing they want is people walking out of their casino because it's dark. And so even though we might not see it that way, they actually probably spend more and are more concerned about reliability than sometimes even hospitals. A lot of hospitals still have one standby generator, but most hospitals of any size that are new, that are built today or refurbished, all have parallel generators. It's critical for the reliability because you just can't afford to be out of power in a hospital. Well, the second reason for using parallel generators is scalability. Let's say that you need 500 kilowatts now, but you're growing and you think you're going to add load in the future. And as you grow, you'll need more power. In another 5 years, you're going to need 1 megawatt. You're going to need 1,000 kilowatts. Well, what do? Well, you could buy a 500 kilowatt generator now. In 5 years, you could sell that generator and buy a 1 megawatt generator. Or you could buy a paralleled system. Well, the other option, of course, would be to buy the 1 megawatt generator now, but that's going to cost you a lot of extra money. So why not just buy that 500 kilowatt generator now, but buy it as a parallelable generator. And that way, in 5 years, you can add a second generator. Makes a lot of sense. Serviceability. Now, you probably know that if you have an emergency generator, changes in the National Electrical Code require that when that emergency generator is down for repair or simply down for maintenance, such as changing the oil in the generator, you need to go rent a portable generator. You bring that portable generator in and you have to buy a permanent means of switching to that portable generator when they build the building and put in your connectors for the portable generator. This is a lot of money, and renting portable generators is very, very expensive. So one of the ways around that is to use more than one generator. If you have 2 generators, then one of the generators remains online while you take the generator down for its oil change. And in the code, it allows you not to have to bring in a portable, not to have those permanent means for connecting a portable, if you have more than one generator and can continue providing your critical power when you bring that generator down for service. So that's money savings, it's a reliability savings, and there are other advantages other than these three. For instance, how about load banking? A lot of people with a generator system like what you see there in the bottom will buy a load bank and put it on the system. And the load bank, let's say each of those generators is 500 kilowatts, so you have a 3 megawatt system. Well, if you had a 3 megawatt generator, you'd have to have a 3 megawatt load bank. But if you have 6 500s, you have a 500 kilowatt load bank, and you simply test the generators one at a time by simply starting the generators one at a time, turning on the load bank, and allowing them to do their load bank test, which we typically like to see once a year. Saves you money, works very well. And that's not the end of the advantages to parallel systems, but that's some of them. So why would you not want to use a paralleling system? Well, you're looking at it. Typically, parallel generators are very expensive. They are very difficult to start up. They're very difficult to maintain. Complicated systems. And we will talk about that in just a moment. So there's your summary of the first part of this presentation. Now, in the next part, we're going to look at just basic theory on how you parallel generators. So before you synchronize, you need to have an electronic governor that can load share. You need to have voltage regulators that can load share. You need alternators with identical winding pitches. You need the same number of phases on the generators, the same phase to phase voltage, and the same phase to phase rotation, or the same phase rotation, I should say. So let's talk about those in a little bit more detail. We're going to look at two generators. One generator is in the solid line there. The second generator is in the dotted line. And you can see in panel one that the voltages of those two generators are different. But we can't parallel generators that are not the same voltage. So this is the job of the voltage regulator. Before we parallel, we're going to take generator 2. I'm going to call the solid line generator 1 and the dotted line generator 2. And we are going to increase the voltage of generator 2 by putting more current, more DC current into the field until the voltage of the two generators match. Now the voltages are the same, but we have a phase angle problem. The two are not in phase. So now we move to our governor, and the governor will put a little bit more fuel into engine number 2 and cause engine number 2 just to speed up ever so slightly until the two can come in phase. And once the two are in phase, then we are ready to parallel, but we have not yet paralleled. What do we have to do to actually parallel? Well, we need a circuit breaker to close. Now, in paralleling switchgear, that circuit breaker is in the paralleling switchgear, generally inside in an electrical room. And in this particular picture that you're looking at, for the paralleling switchgear on the left, the rightmost cabinet is your master cabinet. And then you have two generators, and each of those generators has its own vertical section. The circuit breaker there is on the bottom. If you look up a little bit, you got some lights and switches, and the little controller there is your generator controller. And then above that at the top, you have your ammeter and your voltmeter and your frequency meter. Well, that's been typically how it's done. It's very, very complicated, as we'll talk about in a minute. But there's a new way of paralleling generators called the integrated approach. In the integrated approach, we're taking advantage of the fact that microprocessors are much more capable these days than they were in prior decades. And so we're going to go ahead and put that paralleling contact right on the generator. So you can see there on the right, there's our paralleling contact. We still have a circuit breaker. In the smaller generators where we can, we prefer to use a contactor in order to do our paralleling, and the circuit breaker is simply for circuit protection and to use as a lockout. Once you get into very, very large systems, of course, contactors are not available and you're going to have to use a circuit breaker, but we prefer the contactor where we can. Now that you're connected, now those generators have to stay they have to balance each other. So how do we balance them? Well, like a tandem bicycle, we have to balance two things. We have to balance the kilowatts and we have to balance the kilovars. So the thing that balances the kilowatts is the governor. The governors in each of those generators have to constantly adjust themselves as the load changes to make sure that assuming there's 2 generators, as we see in this example, each of those generators are producing half the power. Now, what if one of the generators is 600 kilowatts and another is 300 kilowatts? Can you parallel those? Well, of course you can. And in that example, we're still going to balance the loads, but it's going to be balanced by percentage. So each of the generators will be loaded to the same percent, even though they may be different ratings. Now, we also have to balance the kilovars. And the way we balance the kilovars is with the paralleling voltage regulator. So they're going to balance the voltage such that each of those generators is producing the same amount of kilovars. Now, what determines how many kilovars are required? In a system like this, where you have 2 standby generators paralleled and feeding a load, the load determines that. The load and the load alone is going to determine the kilovar requirements. And the generator's job is simply to divide those up and to make sure that each generator provides its share of kVAR. Now, if the kilowatts are balanced and the kVAR are balanced, then of course our kVA is going to be balanced as well. Now, these are the quadrants of generator operation, and you can see on the horizontal axis we have our kilowatts, and on the vertical axis we have our kilovars. So normally we want to operate in a position where we're generating kilowatts and we're generating kilovars, and generators are very happy with that. Now, if we move over to quadrant number 2 here on the upper left, that is a situation in which we have reverse power. In other words, instead of the generator providing power, we have power being pushed into the generator. Well, generators don't like that. They like to provide power. They do not like to be pushed. And if you try to push a generator by putting more power into it, then the losses in the generator, it will overspeed and it will trip on overspeed. If we go down to quadrant 3, then it's the same thing. We've got that problem with reverse power, but now we also have a problem with reverse kilovar. Let's go over to quadrant 4, taking a look at the reverse kilovar. Why would that be a problem? Well, it turns out that you push DC current into the field of the alternator, and the alternator produces a voltage. If you put capacitors on the line, then what you would be doing is providing kilovars to the generator. And when that happens, those kilovars provide excitation to the generator, and in order to control the voltage, we have to reduce the DC current going into the field. As you add more kilovar, you reduce the DC current going into the field until you get to the point where the DC current is 0 or too small. And at that point, you lose control over your voltage, and you end up with wildly fluctuating voltages, which will again lead to a generator trip. So generators can take some kilovar, but for the most part, we want to try to make sure that that generator is generating kilovar and not receiving kilovar. Next, we have to have our protection. So if those of you who are familiar with the ANSI device numbers, the ANSI, the American National Standards Institute, many years ago, decided that they were going to write a number for each of the relays. And so they decided that a sync check relay would be a number 25, a reverse power relay would be a number 32, and so on. And that way, when you did a drawing, as you see in the upper right, you could just put a little circle there and write 25 in it, and people knowledgeable in power systems would know that that's a sync check relay without having to write the whole thing out, because there simply isn't room to write these things out on a single line diagram. But a parallel system has to have synchronizing relays, reverse power relays, over under frequency protection, over and under voltage protection, over excitation, volts per hertz protection, instantaneous overcurrent, time delay overcurrent, and so forth. Now, I go back a ways, and in my day, I'm talking about 1980 when I started working, all of these relays were separate relays. They were all mechanical, a lot of them operating on induction discs. And a sync check relay would be one relay, a reverse power relay would be another relay. And so if you'd look at the panels and switchgear, you would see all these relays on the switchgear in these black boxes with glass fronts. Well, along came a kind of a nasty device invented in 1969 called the microprocessor. And it turned out that a microprocessor not only could do this job better, than a mechanical relay, but one relay could do multiple functions. So you could put a 25, a 32, an 81, and so on, all in one relay. And of course, Westinghouse and GE, the manufacturers of these relays, hated that because of all the money they had in manufacturing and testing and calibrating these relays. And so they began to fight that. And I remember papers coming out saying, why would you ever put a microprocessor in a big power system? Well, eventually they lost, and they knew they were going to lose, and microprocessor-based relays are now the standard. So we have taken things that were initially done by many different modules, and it's being done by one module. Well, we saw the same thing in paralleling. Manufacturers used to making paralleling gear, manufacturers used to making big iron, have really fought the integrated paralleling approach. Generac was the first one to come out with the integrated paralleling approach, and lots of people fought that approach and tried to say that you shouldn't use it. That still goes on today a little bit. But eventually it proved, of course, that it was the better way of doing things, and Generac has been extremely successful with that. And other manufacturers like Cat, Kohler, Cummins have all come on board manufacturing their own version of that now. So there's lesson 2 summary. Now, what is an integrated approach to paralleling? This is your master controller. Now, in this particular master controller, you can see on the top we have a PLC, a programmable controller. Allen Bradley, Siemens, Mitsubishi, GE, and that's got a custom program in it. It also has remote I/O out here and lots of inputs and outputs that it can go to the various sensors in this master controller. The next thing down here is a load sharing and a synchronizer. Well, that's nice. You've got 2 things in one box. It can not only do the synchronizing, but it can also control your load sharing. Next one down, we have, our protective relay. And again, this is a microprocessor-based protective relay that's capable of doing many relay functions. So instead of having 6, 7, 8 relays in here, we only have one relay that can do all of those functions. Then we have our voltage regulator, our generator controller, our governor, and so on. And just look in there and look at the amount of wiring, the amount of inputs and outputs and sensor connections and so on. This is a very complicated thing. And I remember when I was at Geneva Steel went bankrupt, and they lost their utility connection. They bought a parallel generator system that had 2 generators on it. They asked me to come down and take a look, see if I could start it up. And I said, there's no way in the world I'm even going to touch this thing. They're very, very complicated. And typically the startup will take maybe a week or 2 weeks. And the person doing the startup, the person doing the maintenance and the troubleshooting has to be very, very well trained and have lots of experience in that particular parallel system. For instance, an ASCO paralleling system would be an entirely different system than some other manufacturer. And so you need to get someone who's very, very familiar and experienced with that particular parallel system because they're complicated. Now let's take a look at these boxes. At the top is a programmable controller. What's in the programmable controller? Well, I would tell you that there's a power supply, there's a circuit board, there's a microprocessor, and there's a program. Well, how about the load share synchronizer? What's inside of that thing? Well, I would tell you there's a power supply, there's a circuit board, there's a microprocessor, and there's a program. How about the protective relay? What's inside of that? Well, there's a power supply, there's a circuit board, there's a microprocessor, and there's a program. I won't go on. I think you get the point. Well, if that's the case, and if we already combined all these relay functions on Run Relay, why can't we combine this entire cabinet into one device? Well, the answer was because nobody had done it. Generac was the first to do it, and here it is. Basically, everything in that entire cabinet now is on one circuit board. Now, where do we put that circuit board? Well, there is no real reason to have an external master controller. Why not go ahead and put all the master control right on the generator controller, and we'll put that on the generator. Now we can completely get rid of the paralleling switchgear. So on this was the first generator controller to use a high-speed 32-bit processor. Everything's surface mount. Of course, we've taken the cover off here, but you can see the seal there, and everything is inside of a metal enclosure, vibration mounts, completely sealed. It's got your PLC logic in there. It's got the generator control in there. It's got your bifuel controller. That would be if you had a generator that ran on both diesel and natural gas. It's got your voltage regulator, your human machine interface, your governor, your auto synchronizer, digital communication, protective relay, load sharing in terms of kilovars, and load sharing in terms of kilowatts, all done on one circuit board. Now, if you're trying to troubleshoot, you can imagine what troubleshooting would be like here. I mean, one wire comes loose, and it's a nightmare to troubleshoot. In a case like this, everything's on one circuit board, and there is not a big terminal connection with a lot of screws. On the back, we simply have connectors, automated connectors. You simply plug this in. And so if you want to replace the entire master controller that includes all of these functions, you simply take out that controller, put a new one in, and plug in your connectors, which are on the back, not shown. And voila, you've replaced the entire system. So a huge advance in paralleling of generators. Let's go now through a sequence of paralleling of generators. We're going to assume that we have two generators and we have two transfer switches. One of the transfer switches supplies critical load and the other transfer switch supplies equipment load. The red color indicates what's energized, so we have them energized from the utility. The next part of our sequence, we will cause the utility to fail. In that event, each of these transfer switches is going to close a contact, our typical 2-wire start, and it's going to go over this dotted line. So if either of those transfer switches sees a power outage, it will close a contact to the system controller, and the system controller will then realize that we need to start the generators. Then this second dotted line between the system controller and the generators is a communications line. In this 2004 version, that was Modbus and twisted wire pair. In the newer controllers that Generac is producing, this becomes an Ethernet connection. But we'll just say it is a communications connection. It causes both of those generators to start. So there they go. Now the first generator that comes up to speed and is at the right voltage and the right frequency goes ahead and closes its contactor. The second generator has not yet closed. So we only have half of the generation available, and in our example here, we're going to assume that that is not enough power to operate both our critical load and our equipment load. So we're only going to close the critical transfer switch. Now you can see that generator number 2 sees the power on the bus because it's right there on the other side of that contactor, which we're showing as a switch, but it's actually a contactor. So since it's all of the synchronizing, all the load sharing, everything is right in the generator itself, it goes ahead and synchronizes, and it will do that generally within 1 to 2 seconds. At that point, it goes ahead and closes. Now we have full power on our system, and the equipment transfer switch closes. Now let's assume that we haven't been filling our fuel tanks correctly and generator 2 runs out of fuel. In that case, generator 2 is going to open and we will trip our equipment transfer switch to neutral. Now we go back to generator 2, put fuel in it, restart it. It comes up, it synchronizes. We close the equipment transfer switch, and then our utility comes back. Once the utility comes back, then the transfer switches are going to time out. They're going to give the utility a little bit of time to make sure it's steady, and then they will go back to the utility. At this point, we go into our generator cool down, let the generators cool down, let's say 5 or 10 minutes, and then we will go ahead and open those generators. And we're back to where we started. Now, I told you that the purpose of all this parallel generator things is mainly redundancy. So you may be looking at this and saying, okay, I've got redundant generators, but what about that system controller there? Why is that system controller there? Because if that system controller goes out, I've lost my entire system. And the way this is drawn, you are correct. But the way the system actually works is not that way. Think of the system controller as a big remote enunciator. Now, it's a fancy remote enunciator. It's got a big touch screen on it. It shows a diagram of all the generators. It shows your total system kilowatts, your total system kilovars. It shows any generators that have failed and the alarms that are in those particular generators, and on and on. So it's a really nice remote enunciator. But it does not do the paralleling. It does not do the synchronizing. It does not do the load sharing. And so what I typically do, that's not shown on the diagram, is take this 2-wire start from each of the transfer switches and go ahead and wire it to each of the generators. So this is pretty easy. We just daisy chain, and we take a twisted wire pair from the system controller to the generators, and then we take 3 more wires, although it looks like there should be just 2. And we take those to the generators. Now, the generators are constantly talking to the system controller, and if the system controller fails, if you go in with a pair of scissors and literally cut the communication line between the system controller and every generator, it doesn't matter, because the generators will see that the transfer switches are calling for power, and since the system controller is down, then they will ignore the system controller and go ahead and do the paralleling themselves. So the fact that the system controller is down does not mean that the system is down. Now, you do lose your big remote enunciator. Now you have to go to each generator to see what's going on, because you don't have a nice digital display that shows the whole system. But you have that first level of redundancy. There is also a second level of redundancy. If you want to, you can go out there and just start generator 1. You do that by turning the switch to manual. So there's auto, off, manual. You turn it to manual, boom, the generator starts, and then there's a little button on the screen that says manual mode parallel. You push that button. That's all that's necessary in order to parallel that generator to the system, and that's all that's all that you can do. We don't let you go in and fix this thing. A lot of times they use the analogy of a DVD player. I don't know how DVD players work. Yeah, I know there's lasers in there and they bounce this, but I don't know the codes and all that. I couldn't go in there and make that work. But guess what? I don't really have to. All I have to do is push the little eject button, put my disc in, push that same button again. It goes in and loads the disc, and then I press play. And that's the same way with this system. Is it complicated? Yeah, of course it's complicated. It's very complicated. But not only do you not need to understand the complications, we don't even let you into those areas. The only thing you can do is push a button and say parallel, and then it does everything automatically. Way, way simpler than the paralleled options that we have had in the past. Now, how fast does this happen? Well, turns out that in paralleled switchgear, you basically start a generator, you put the power onto the bus. We call this whole process dead bus arbitration. And then you synchronize a second generator to that, and then you close that, and then you synchronize the third generator to that, and you close that. And it will take 30 seconds, maybe a minute, to bring up a large system. But in this case, all of those generators all have the master controller right in the generator controller. Synchronization and paralleling is done very, very quickly. So typically what you will have is you have a power outage. All of a sudden, all the generators start, and then it will be maybe 5 seconds before all those generators are up and stabilized and producing the right voltage and frequency. Then the first one that arrived will go ahead and close. And once the system bus is energized, then all of the others synchronize and parallel independently. So you will hear, and then it'll stop, and then you hear click as the first contactor clicks, and then all of the rest of them synchronize. It takes a second or two, and then you hear, and all of the other generators parallel. Our system at the University of Utah, I'll show a picture of that, has 10 generators in parallel. Typically from power outage to all generators online and parallel is approximately 7 seconds. And that's kind of unheard of with traditional paralleled systems. Okay, integrated versus traditional. Not going to get into this in tremendous detail because I think we have talked about it as we have gone along. Here's a system which has one master controller and then 3 generators. You can see it's very large, it's very expensive, it requires a building to be in, and none of this is necessary. We have the whole master controller on the circuit board that gets rid of the master section, and we simply put these contactors or the circuit breakers on the generator. Now you just get rid of this. There's really no reason for paralleling switchgear with today's modern control systems. What are the limitations of that? Higher capital cost, higher installation costs, space constraints, complexity, installation time, and commissioning time. Now, we typically try to use breakers, or excuse me, contactors rather than breakers when we can, because breakers are intended to protect circuits from overcurrent. Contactors are meant to close and open a lot of times. So if you have a motor starter, you tend to want to use a contactor in that motor starter, and upstream of the contactor is going to be a breaker to protect the wiring or a fuse switch, and we use the same thing in our generators by using a contactor where we can. Now, when you get into really big generators, you simply can't get those contactors, so we go to a circuit breaker because there's not much choice. This is typical of parallel switchgear. There's a master controller. There is other controllers then on the line, and 4 to 6 controllers in each section for generator 1, 4 to 6 controllers in each section for generator 2. Very complicated system, all of them having to talk to one another. And this is a picture which I think we have gone through in quite a lot of detail. You've got custom hardware, custom software, very difficult to troubleshoot, multiple suppliers of equipment, custom programs, hard to troubleshoot, hard to calibrate, and that's all replaced by a standard system. Now, this is not what the Generac system looks like inside, but this is a block diagram showing basically what these things look like, and we're showing op amps there and resistors and so on. Of course, the Generac system is fully digital. Once you have all of those things on one board, in addition to making it cheaper and simple and easy to work with, it also makes it a whole lot less costly. So you get reduced interconnecting wiring, proven hardware and software, no custom software. You don't have any calibration issues. Everything is digital. It enhances load balancing. You get improved tolerance to electrical noise. A lot less wiring helps your electrical noise. Reduced system failure modes, higher reliability, and the system remains operational regardless of what fails. There is no single failure point in this system. So there you have your traditional approach. There you have your integrated approach. As I said, Generac was the initiator of that, has more of these systems installed than anybody else, and they were the pioneers. But it has been so successful that pretty much all the major suppliers of generators have now developed a system that can do that. So we're back to reliability. You would never put a single engine on a jet because the jet would crash, so we always have redundant engines. And there's many places in society where we use redundancies, like redundant processors on this space shuttle. Some people will say, well, I want 2 batteries in my generator because that enhances the reliability, or 2 starters. Well, why don't I have 2 generators? And the fact is that with 2 generators, you, in most cases, 2, 3, 4, 5 generators, this may not sound logical, but it's actually less expensive. That's because if we look at dollars per kilowatt on a diesel generator are the lowest in the 400 to 600 kilowatt region. So below 400 to 600 kilowatts, it costs you a little more per kilowatt in order to generate that kilowatt. And as the generator gets larger and larger, then you get a lower dollars per kilowatt. Once you go above 600, now you're talking about what we call big iron, things that are not commonly used in over-the-road trucks and front-end loaders and so on. And so you end up with a lot of handwork, the profit margins are higher, and your dollars per kilowatt then goes up. So we had a project it was actually a chicken hatchery. They went out for a quote on a 2 megawatt generator, and we quoted that, but we offered them an alternative for 5 parallel generators, 500 kilowatts apiece. And we got an order right away, which is not typical. I think that's maybe the only project I can ever remember where I got an order that fast. Turns out they thought we had made a pricing mistake, and they wanted to hurry and get us to accept the order before we figured out that we had underpriced it. Well, we didn't underprice it. 4 500 kilowatt generators is significantly less expensive than a 2 megawatt. It's easier to install. It's easier to maintain. It is easier to get parts for. It's easier to troubleshoot. And it turns out that with those, the actual load on the plant when we had our first outage was about 900 kilowatts. So we actually have N+2 redundancy. And you know, what's not to like about that is just so many advantages that you would not have gotten with the 2 megawatt generator. And this is fairly typical. People buy an MPS system that's called modular power system in order to get their get the reliability and so on. They end up with redundancy, even though they didn't buy it. Here's another example of one that we did for a water treatment plant. They wanted a 1500 kilowatt. We supplied 3 500s, and it turned out the total plant load during the first power outage was under 1,000, so they have an extra generator. This one down on the bottom is your University of Utah, and you can see here these are called Geminis. They actually have 2 generators inside of an enclosure. Now, the only thing common to that is the enclosure and the fuel tank. The generators each have their own engine, their own alternator, their own circuit breakers, their own controllers, 2 completely separate engines. So you can see 1, 2, 3, 4, and there's one back here, 5. That's 5 Geminis, 10 engines, and they start in about 7 seconds. Now you can see they have 6 more pads, and that is for phase 2 when they will need to increase the power on the system. Total owning costs, it's actually generally a little bit cheaper to maintain a standby system with multiple generators than it is one big generator, because those big generators have a lot of oil, their air filters or fuel filters, all those things are kind of custom, very expensive. Easy to crane into place, pad thickness is down, more manageable, and so your total owning costs generally are going to be lower than on a single engine. Footprints, typically multiple ones are going to be slightly bigger, but we do have installations where they actually were smaller. And you can see in this instance, I think that's kind of pretty. This is not ours, but they really didn't have any place to put the generators, and they lined them all up end to end, which is no problem. We have a number of instances where those generators are lined up end to end like that. Serviceability, again, we talked about the fact that an emergency generator, that's one that's important for life safety. You can maintain 1 generator at a time. You don't need to bring in a portable. It's much easier to service, and you maintain your power supply while you're doing that service. And so we're up to our lesson 5 summary, and that's where we're going to stop for the day. So I thank you, and we are open to questions. I would like to turn the time back to our host, Mr. Tyler Simmons.
Great. Thank you, Craig. We do have a couple questions here. Let's start with, when paralleling generators, do you typically see them having similar fuel consumption? If not, does it indicate a problem?
Yeah, we definitely see them having similar consumption. And if you had one generator consuming a lot more fuel than another in a parallel system, that would be reason to investigate, because the loads on both generators should be just virtually identical. And you know how this is. If you look at a generator, just look at one generator on a system, the load's always going up and down a little bit as things change. And if you look at parallel system, the load is always going to change a little bit, but it's the all those generators are going to be dialed in to where, although they're going up and down a little bit with the load in the power plant, they're going to be just really close in terms of the paralleling. So a similarly sized generator with a similarly sized load should pull approximately the same amount of fuel.
All right, there's another question here about whether generator paralleling would affect maintenance scheduling. I'm guessing they're referring to how often you schedule or anything like that.
Oh, okay. In terms of how often you schedule, then it's pretty much the same. I mean, I think regardless of the size of your generator, we typically recommend maintaining a generator every 6 months. And on 1 6 month interval, well, you should go out every month and just check the generator. This is generally a user that does this. And feel the engine, make sure it's warm, make sure the battery's good, the battery charger's on, look and see if the controller shows any faults, things like that. That should be done monthly. And then in 6 months, we recommend that someone who is a trained generator maintenance guy, and in some big facilities, they do their own maintenance. In most places, they will hire someone who is a generator company to do that maintenance. And we basically go out, we hook our laptop into the thing, we take a look and see if we've had any faults from the past. We, again, check things like batteries and battery chargers and block heaters, and there's, like in your car, we do a number of checks there, but we don't actually change the oil or anything like that. And then 6 months later on the year, we would go ahead and change the air filter, change the oil filter. If there's any water, let's say, in any of the fuel filters, we would drain those, and we would do the kind of, what you do on your car when you take your car in for an oil change. Now, if you look at the air filter and it's clean, then of course you don't have to change it, but we would always check the air filter. So your yearly maintenance is more in depth than every 6 months, and pretty much this is the same regardless of whether you have MPS or single engine. Now, in terms of maintenance scheduling within a facility, if you do your own scheduling and you decide to maintain one generator a week or something in a parallel system, well, that's fine. You have more flexibility there in order to determine when you maintain each of those generators. So I hope that answers the question, if I understood it correctly.
All right. Is it possible to perform peak shaving with generators set up for paralleling?
Is it possible? Yes. Is it practical? Typically not. Typically, now let me give you an example that we have. We test motors. We have a motor rewind shop, and when we test a big motor, it takes a lot of power, and therefore it's going to set a peak for the month that would cost us a lot of money. So what we actually do is fire up our standby generator, and then we use that standby generator in order to test that motor, and that way the motor's being tested on standby generator power rather than utility power. And so if you have a generator and you can switch some loads to the generator during a peak time, then that's really easy and simple. And can you do peak shaving? Yeah, absolutely. And we do this all the time. It's becoming very popular that the utility will actually pay you to get off their system during peak times. And if you see peak shaving come up, you can do that. But the simple way to do it is to transfer some of your loads to the generator in order to avoid setting that peak. Now, if you might mean that you want to actually connect those generators to the utility, can that be done? Well, it can, but now you're talking about a lot of complication. And anytime you want to connect to the utility, they're going to require an interconnect agreement and lawyers and all kinds of relays, and it gets very complicated. So I'm not saying it can't be done. And if you have really, really big generators and you want to do this all the time, that makes sense. But for the most part, it's simply too complicated and too expensive to do. And so we accomplish peak shaving by simply removing some loads from the utility and putting them on the generator in order to avoid setting that peak. And that's really easy to do.
All right. We've got another question. I'm currently adding a manual transfer switch with a quick disconnect panel to an existing ATS with a permanent generator. When the permanent generator is disconnected for maintenance or other reasons, we plan on connecting a portable generator through the quick disconnect panel for emergency power backup. Is this design common, and do you have any recommendations or know of any issues I may experience?
Yeah, that design is very common. In fact, A lot of times when you have small facilities and small generators, it probably doesn't make sense to go the paralleling route. The smallest natural gas generator that we make as standard to parallel is 100 kilowatts. The smallest diesel generator is 300 kilowatts. And we can make generators smaller than 300, but like a 200 kilowatt generator parallel is about the same price as a 300. So if you have smaller generators, then you may choose to want to go ahead that route and bring in rentals. Now, what you're doing is very typical of emergency systems, and it was one of those things that I said you can avoid that if you go with parallel generators. But if you need that, then of course it makes perfect sense. What problems will occur here? Well, you need to worry about grounding. That's kind of an issue. You need to make sure that where you plug this thing in, we typically use cam locks, make sure that they're all color coded, and make sure that we get the right phase relationship and so on. One of the problems with that is that most people who do this, you have an automatic transfer switch, and when that sees a power outage, it's going to start the generator, and then the generator runs. When the power comes back, it stops the generator, and all that's automatic. Well, when you come in with a portable, now it's not going to be all automatic because you don't have that same automatic 2-wire start. And I'm not saying you can't do that, you certainly can. But if you feel like the system has to start and stop automatically when no one's there, then you're going to have to take your 2-wire starts from the transfer switches and so on and figure out a way to wire them into the portable generator. And of course, all this creates a little bit more complication. But other than that, what you're doing really sounds like the right way to go.
Okay. Can you parallel generators that are different brands?
Yeah, the simple answer is no. Now, if you have paralleling switchgear, then the answer is yes. But it's going to be very expensive because you're going to have a company that writes, completely different code for one generator versus another. And so typically, even with paralleling switchgear, we try to parallel the same brand. In terms of an integrated approach to paralleling, you really need to stay with the same brand because it's going to be two completely different communication systems, and you can't take a cat and parallel with a Cummins or take a Cummins and parallel with a Generac. It just doesn't make sense. And so in general, it's going to be cheaper and better if you take that existing generator, put it on the market, sell it. Generators have very good market value because a lot of people are looking for used generators, and then put in 2 generators or 3 or however it is of the same brand. Typically, you want to parallel generators only of the same brand.
Does paralleling reliability change by fuel type, natural gas, propane, diesel, etc.?
Could you read that one more time, Tyler?
Yeah. Does paralleling reliability change by fuel type? So is it more reliable on natural gas or propane or diesel?
Okay, thank you. The answer is, if you look at paralleling itself, paralleling diesel has exactly the same reliability as paralleling natural gas. However, there are some problems with diesel. The first is that the number 2 reason for generator failure is diesel fuel systems. This could be water in the diesel fuel. It could be biomass in the diesel fuel. It could be sludge in the diesel fuel. Many times it is clogged diesel fuel filters. So that is a reliability problem for diesel that does not exist with natural gas. The second problem, particularly in an event like a Hurricane Katrina or something, you can't get diesel. And the roads may not be passable, but even if they are passable, we don't have enough diesel trucks to go around and fuel all the standby generators. And so typically, if you're maybe a hospital or a 911 call center, the government's going to go in and they're going to prioritize certain critical loads. You're not going to be able to get diesel fuel. In a place like Hurricane Katrina, the natural gas never stopped. And even in earthquake zones, typically the natural gas will still be there. So although the paralleling has the same reliability, statistics have shown that in an event such as an earthquake, a flood, a tornado, what have you, a natural gas generator is more likely to run and more likely to be operational than a diesel generator.
Okay, last question here. Is there a minimum load percentage that generators need to be operating at? And does that often become an issue when paralleling?
Yeah, it's never an issue when paralleling. Generators, all they do is sync to the voltage, and then once they close, they share the load. And so it's very, very common for you to exercise the generators. In that case, let's say you have 5 generators, you bring them online, you parallel them all, they all run at no load for half an hour, and then you shut them down. That's common. It's the most common way these things are done. So the load has nothing really to do with the paralleling. It's fine. Now, there is an issue there, and that has to do with wet stacking. Now, wet stacking applies to diesel generators, not to natural gas and propane generators. But if you run a generator extensively under 30% load, eventually it's going to wet stack. That causes the power to go down and eventually will ruin the engine. That is not a problem with parallel generators. It's a problem with diesel generators, and it doesn't matter whether they're paralleled or not. So we generally recommend that once a year, sometimes once every 2 years, you bring in a portable load bank and you run those generators at full load. Wet stacking is caused by carbon deposits, and so we load bank them. We get all those carbon deposits burned out, and we can restore that engine to like new condition. And this is actually an advantage of parallel generators, because if you have a number, even 3 or 4 parallel generators, it kind of makes sense to buy a load bank, because the load bank only needs to be big enough for one of those generators. You can load bank them one at a time, and it actually becomes cheaper than hiring someone to bring in a portable load bank and test it like that. So hopefully that answers the question.
We have quite a few questions that have come in here. The first question we had, I'm currently adding a manual transfer switch with a quick disconnect panel to an existing automatic transfer switch with a permanent generator. When the permanent generator is disconnected for maintenance or other reasons, we plan on connecting a portable generator through the quick disconnect panel for emergency power backup. Is this design common, and do you have any recommendations or know of any issues that you may experience?
Yeah, not only is it common, it is pretty standard, and we do that a lot. As I said, in an emergency generator, you need to basically have that set up, and so typically you're going to have a transfer switch that will transfer between utility and your emergency generator. But then if the emergency generator, you're taking it down to change the oil, you either need to have another transfer switch, which is more of an ASCO way of doing things, or you could have a panel which actually opens a breaker to your generator, your permanently mounted generator, and connects in a quick disconnect panel with the ability to just connect cables to the connectors there. And that's a standard way of doing it, and it works great, and it's exactly the way it ought to be. Now, where this gets complicated is this going to start and stop automatically? For instance, if you do this and then you don't get all the maintenance done, or maybe you have a generator that's out for repair, and so you bring in a portable, if the power goes out, is it going to start that portable? Well, it's not, unless you put in the additional controls necessary to do that. And so that's where this all gets a little bit more complicated. And certainly that can all be done. But that's a standard way of doing it. And if you have a smaller generator, that's exactly the way I would do it. But if you have a system big enough for parallel generators, then you can avoid all that by going the parallel route.
Great. Next question is it likely to add capacitor banks to the paralleling generator buses to improve power quality?
So you have to be very, very careful with capacitor banks. Capacitor banks create leading power factor. Now, it turns out that generators can, if you ask most generator manufacturers, they say, no, we can't take leading power factor. You need to make sure that the power factor is not leading. And clearly, capacitors can cause a leading power factor. However, if you want the actual truth, generators can take a limited amount of leading power factor, but not a lot. And if you put too much leading power factor into the system, the generator will go unstable and trip. And obviously, if you've got permanently mounted capacitors online, then when you bring on that first generator, those capacitors can't supply more leading K-bar than that one generator can handle. And so typically with capacitors, if you're using capacitors for increasing your power factor, in general, it's best to put a contactor on there in order to take those capacitors offline when you're operating on a standby generator. Or the other option is simply put the capacitors on the line side of your transfer switch. In other words, put it on the utility side of the transfer switch. And that way, when the transfer switch switches to the generator or to the emergency position, then the capacitors are no longer there. So we certainly can accommodate capacitors. It's just that you got to kind of take a careful look. They can cause a lot of problems.
Next question is, how much time do you lose, or how much longer do you sit in the dark if you don't have a system controller? How long does it take for the generator to realize that the system controller is not functioning?
Yeah, great question. The answer to that is virtually no time at all, because the way I've presented it as the generators talk to the system controller and they say hello and nobody answers, then they take over. But the truth is the generators are always talking to the system controller. And so anytime you lose communications, the generators automatically switch into the backup mode. So you will start in parallel without a system controller just as fast as you start in parallel with one, because the paralleling is on the generators, not in the system controller. Now that is not the case with switchgear, with paralleling switchgear, but it is the case in the integrated approach.
Okay, what about, where does a rotating rectifier fit in this system? I think that must have been talking about when you were talking about the number of engines and redundancy.
Okay, yeah, so just a little bit of background. You know that in order to generate power, you have to have a magnet. And on standby generators, the way you do that is you generate DC current. The DC current goes into the field of the alternator, which is the rotating part, the rotor, and then that creates a magnet and you generate output voltage. So a rotating rectifier basically is used mostly in a DC brushless system where you're putting in AC and the rectifier creates DC out of that. So whether you have one generator or you have multiple generators, that's the same. Every single generator, for instance, in the Gemini, I told you I had 2 generators in each enclosure, but that's 2 separate engines and 2 separate alternators and 2 separate generator controllers and 2 separate batteries and so on and so forth. So the only thing they share is the enclosure. And so we would have a rotating rectifier on every generator in the system, and that's just an integral part of what is typically a permanent magnet brushless alternator.
Okay, next one is, if you parallel 2 generators to the grid, should the K-bar be balanced between all 3 sources?
That's a very interesting thing, and the answer is, if you're going to go to the grid, you can do whatever you want. The utility is generally responsible for providing K-bar to the customer. They got some customer somewhere, it's taking a certain amount of K-bar. That's the responsibility of the utility. And so if you wanted to get the most bang for your buck, you would have 1.0 power factor where you connect your generators to the system And that way you're only supplying kilowatts to the utility and not kilovar. However, there may be a situation in which the utility wants you to provide some of that backup support, and they want you to provide some kilovar to the system. In a parallel generator system that's not connected to the utility, the load determines what kilovar is needed, and then each of the generators simply supply their share of that. In a utility system, then all of that is controllable. And typically, if I was going to provide some free kVAR to the utility, yeah, I would try to balance it between the two generators. But the utility obviously has its own requirements, and I wouldn't give them free kVAR unless they paid me for it.
Okay, great. Next question is, how does cross-current compensation come into play with generator paralleling?
So cross-current compensation has to do with analog paralleling systems. And what I would say basically is all this has been replaced by a digital program. And so the digital program does all of this and does all the controls digitally and controls the kilowatts and the kVAR and the voltage and keeps everything stable. All of that's done digitally. We don't use really cross-current compensation in a digital system. But cross-current compensation was a way of getting analog systems in order to share load. So it's kind of not applicable in this particular system.
Okay, next question. If the system will function without the central controller, what is the benefit of using it? Seems like an unnecessary cost.
Right. So the first thing is the cost is low. The system controller that we use here is about 30 inches high by 24 inches wide by 8 inches deep, and it's got a touch screen in there. So when you go in and you look at the touch screen, you will see all the generators on there. You will see your total system kilowatts. You will see your total system kilovar. You'll see your total system power factor. If any one of those generators stops, it will turn red and you will see that that particular generator stopped. So this system controller is your window into the entire generation system. And I think you're definitely going to want to see that because you want to see what the whole system is doing, not each individual generator. The second advantage of the system controller is that it will keep you isochronous right at 60 hertz. Whereas if you don't have the system controller, you're going to be not right at 60 hertz. You may be at 59.95 or 59.9 because the generator's in droop mode, and you're going to be close to 60 hertz, but you won't be right at 60 hertz. So if you want it to be just exact, then you're going to system controller is a good way to go. But the primary reason we use a system controller is just having a touch screen that lets you walk up inside the building and see what the entire generation system is doing. And it's a very low cost compared to that functionality that it provides.
Great. Next question is, are the Generac paralleling controllers available for retrofitting on existing generators?
Yeah, that would be great. The answer is, in theory, yes, but practically no. For instance, we had some generators up at Hill Air Force Base, and they had older controllers and we retrofitted them. And so it is possible. But the problem is when you put on a new controller, you've got to make sure that all of the sensors in that controller are correct. For instance, your tank level sensor and your speed sensor and so on. And you may actually have to go in and change some of those sensors out. You may have to change out wiring harnesses in order to get those in there. And when you put a new controller in, the controller for the generator is not the same as the engine controller. Typically, the manufacturer of the engine is going to have a separate controller on the engine from the generator controller. And so you've also got to have all the communications between that particular engine and the generator. And so the result is, no, you're really better off buying a new system and selling the old one than trying to retrofit. We have never retrofitted one because when you look at the cost, it's just not worth it.
Okay. Next question is, can you please discuss choosing the redundancy change based on different load types like lighting or data center loads or et cetera, different loads?
Yeah, one of the things that's very interesting about this system is that a lot of time you get N+1 redundancy without realizing it or without designing it into the system. And give you an example, we had a water treatment plant that wanted a 1,500 kilowatt generator, and we sold them 3 500s paralleled. Well, when they had power outage, it turned out that they didn't need more than 1,000 kilowatts, so they actually have an N+1 extra generator, and so they have full redundancy. And they didn't really buy it that way. They would have bought just a single 1,500 kilowatt generator, but by doing it this way, they got redundancy because the load was not what they thought it could be. And this is kind of typical. When you size generators, most generators are about 50% loaded. That's because when we calculate what's needed, we always assume that all the motors are running, they're all running at full load and so on. And we just end up buying more than we actually need. So that's one issue that you don't learn about till after the fact. Now, in terms of redundancy, you have to look at, again, what are the criticality of your loads? If you have a data center, for instance, you're going to need all those loads to run all of the time. And so N+1 is the way you want to go. So if you lose a generator, you still have full power. But in other commercial areas, you may need your data center to run, you may need your building evacuation and your elevators to run, but in an emergency, you'd like to have the air conditioning, you'd like to have the lighting, you'd like to have other loads operate. Maybe you're in a hotel, you'd like to have all of the rooms fully operational, but in the event that you lost a generator, you may say, well, in that case, I'm going to be okay with not powering some of those less important loads so that I can make sure that I have redundancy on the critical loads.
Great, thank you. Next question is, how is it best to integrate the load banks for operating scenarios where the plant load is below a minimum generator load?
So first of all, let's talk about what the minimum generator load is. According to NFPA 110, the minimum generator load on a diesel generator is about 30%. Now, there isn't actually any minimum generator load. Generators are happy to produce zero load, and on natural gas generators, we don't mind that. But on diesel generators, if you operate for long periods of time below 30% load, you get what's called wet stacking. And wet stacking will reduce the ability of your engine to carry full load, and eventually it'll ruin the engine and require a complete engine rebuild. So one of the big advantages of paralleled systems is to be able to buy a permanently mounted load bank. Now, if you have one 2 megawatt generator and you want, generally if you're going to load bank that, you want to bring that up fully to 2 megawatts, get it as hot as you can, and I shouldn't say that, not as hot as you can, but you want to get it up to full load so you get it up to full temperature and basically make sure you get rid of any wet stacking. If you have 4 500 kilowatt generators, then what we would typically do is we would take those 4 500 kilowatt generators and we'd take them to a panel board. And in that panel board, you could have an additional breaker that has a load bank on it. And so now you don't have to have a 2 megawatt load bank. You only have to have a 500 kilowatt load bank. And what you do is you would start one of those generators, only one, and then you would turn on your load bank and do your load banking. And then you would have a situation where if you had a power outage and the transfer switch switched to the utility, remember that panel board on the generators is not going to be connected to the load because it's going to be on the emergency side of the transfer switch. And so when you switched, then you would simply have a dry contact that would tell the load bank to shut off. Now, some people say, well, we want to make sure that if we run for long periods of time, We want to make sure that our load bank is providing enough to keep the generator above that 30% load. Very seldom is that the case. I would say generally you don't worry about that and you just load bank your generators about once a year. But if you wanted to do that, you can put CTs and kilowatts measurement devices, power measurement device on there, and then you can get an automatic load bank control that will just give you as much load bank as you need to stay above that 30% value. Hospitals get a little bit more complicated here, but in general, that would be my recommendation.
Okay, looks like our last question for now. If you've got any other questions, please feel free to shoot those in quickly while Craig answers this question. It's a follow-up on the central controller question. Does the central controller provide the means for SCADA systems to pull data out of it, such as power parameters and status?
Great question. So the controller that was introduced back in 2003, which is the one I've been showing you, has a Modbus port, and that Modbus port will typically talk to anything that you want to talk to it via Modbus. We also have a newer controller that's coming out that's beginning to replace that. It will have Ethernet as standard. Now, if you decide that you want that on that other controller, if you wanted Ethernet, you just get a little gateway that goes Modbus to Ethernet, and it's easy. Now, that thing can pull out everything. So for instance, let's say that you have a low fuel on generator 7. Well, when generator 7 has an alarm, then it will send a message to your system saying, I have an alarm on the system, and here's the alarm. It's a low fuel warning on generator 3. You can also go in there and just get operating system data. So if you have a SCADA system, yeah, I'd like to know how many generators are online. I would like to know what the kilowatts is on the whole system, what the kilobars on the whole system is, what the did I say kilobars, what the power factor is on the system, and the status of the system if there are warnings and so forth. All of that's available, just like any other communication system. It's just in registers. And so you just go read the registers, and yeah, all of that is available.
Great. It looks like there aren't any more questions. So I want to thank everyone for joining us today. And thank you, Craig, for doing a wonderful job on helping us understand paralleling and generators. Thanks, everyone. Have a great day.